Hi, and welcome to the class on probability as part of the statistical inference class in the Coursera Data Science series. My name is Brian Caffo, and this class is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Bloomberg School of Public Health. In this lecture, I'm going to cover probability at a very basic level, just enough for what we need in the data science specialization. I have a more in-depth treatment in my Mathematical Biostatistics Bootcamp series. You can watch them on a YouTube playlist anytime you'd like, and then the course is offered about every 2 months on Coursera, and I give the link here. In addition, the course notes are on GitHub. Let's talk about probability. So given a random experiment, say for example rolling a die, a probability measure is a population quantity that summarizes the randomness. I want to emphasize this word population here. What this means in the die roll context is that we think of it as an intrinsic property of the die, not as something that is a function of a simple set of fixed rolls of the die. So when we talk about probability, we're not talking about something that is in the data that we have, but as a conceptual thing that exists in the population that we would like to estimate. So let's be specific about the rules that probability has to follow, so-called probability calculus. First of all, probability operates on the potential outcomes from an experiment. For example, when you roll a die, you could get a 1, or you could say the roll was in the set, 1 or 2, or the roll was an even number, 2, 4, 6, or the roll was an odd number, 1, 3, 5, and so on. So the probability is a function that takes any of these sets of possible outcomes and assigns it a number between 0 and 1. You have to have the rule that the probability that something occurs, in other words, that you roll the die and you get a number, must be 1. And then the probability of the union of any two sets of outcomes that have nothing in common must be the sum of their respective probabilities. So for example, when I roll the die, one possible outcome is that I get a 1 or a 2. Another possible outcome is that I get a 3 or a 4. Those two sets, 1 and 2, and the other set, 3 and 4, are mutually exclusive. They cannot both simultaneously occur. The probability of the union that I get a 1, a 2, a 3, or a 4 is the sum of the two probabilities. The sum of the probability that I get a 1 or a 2 plus the sum of the probability that I get a 3 or a 4. It turns out that these simple rules are all that are necessary to generalize to all the rules that we think probability should follow, and this was discovered by the Russian mathematician Kolmogorov. Here are some of the rules that probability must follow. Some of them I stated already, and some of them are consequences of what I stated already. The first is the probability that nothing occurs is 0, so you have to roll the die. Something has to occur. You have to get a number. And that's similarly related to the probability that something occurs, that you do get a number, is a 1. Something that we intuitively seem to know is the probability of something is 1 minus the probability that the opposite occurs. So the probability of getting an even number when I roll the die is 1 minus the probability of getting an odd number, because the odd numbers are the opposite of getting an even number in the context of a die. The probability of at least one of two or more things that cannot simultaneously occur, we call sets of things that cannot simultaneously occur mutually exclusive, is the sum of their respective probabilities. This was part of the basic definition that we outlined in the previous slide. Another consequence of our probability calculus is if the event A implies the occurrence of the event B, then the probability of A occurring is less than the probability that B occurs. And this is kind of a tongue twister to say, and it seems a little bit conceptually hard. However, if we draw a Venn diagram, it becomes very simple. The event A lives inside of the event B. So when we talk about the probability of A, we talk about a number assigned to this circle, A, and when we talk about B, we talk about the probability assigned to this circle that includes the area of A, so it would make sense that the probability of B was larger than the probability of A. So I think we intuit this very easily. For example, the probability that we get a 1, the set A, is less than the probability that we get a 1 or a 2, the set B. Then this final bullet point is very useful. For any two events, the probability that at least one occurs is the sum of their probabilities minus their intersection. Again, this becomes very easy to visualize with a Venn diagram. Here we have the set A, and we have the set B. If we add their two probabilities, you see that we've added the intersection in twice. Once when we added in A, and once when we added in B. Since we've added it in twice, if we want the probability of the union, we need to subtract it out once. The result of this rule is to say that you can't just add probabilities if they have a non-trivial intersection. And we'll give an example of that in a second. The National Sleep Foundation reports that around 3% of the American population has sleep apnea. They also report around 10% of the North American and European population has restless leg syndrome. Let's assume for the sake of argument that these are probabilities from the same population. Can we just simply add these probabilities and conclude that about 13% of people will have at least one sleep problem of these sorts in this population? So the answer is no. The events can simultaneously occur and so are not mutually exclusive. We think that there is a non-trivial component of the population that has both sleep apnea and restless leg syndrome. So to elaborate, let's let A be the event that a person drawn into this population has sleep apnea, and B be the event that they have restless leg syndrome. Here we think this intersection is non-trivial, and so if we were to add the two probabilities, we would believe we will have added it in twice, and it would need to get subtracted out to find the probability of the union. In this slide, I simply show you the notation. So probability calculus is useful for understanding the rules that probability must follow, and forms the foundation for all thinking on probability. However, we need something that's a bit easier to work with for numeric outcomes of experiments, where here I'm using the word experiment in a broad sense. So densities and mass functions for random variables are the best starting point for this, and this is all we will need. Probably the most famous example of a density is the so-called bell curve. So in this class, you'll actually learn what it means to say that the data follow a bell curve. You'll actually learn what the bell curve represents. Among other things, you'll know that when you talk about probabilities associated with the bell curve or the normal distribution, that you're talking about population quantities. You're not talking about a statement about what occurs in the data. How this is going to work and where we're going with this is that we're going to collect data that it's going to be used to estimate properties of the population. Okay? And that's where we'd like to head. But first, before we start working with the data, we need to develop our intuition for how the population quantities work. A random variable is the numeric outcome of an experiment. So the random variables that we will study come in two kinds, discrete or continuous. Discrete are ones that you can count, like number of web hits, or the different outcomes that a die can take, or even things that aren't even numeric, like hair color, and we can assign the numeric value, 1 for blonde, 2 for brown, 3 for black, and so on. Continuous random variables can take any value in a continuum. The way we work with discrete random variables is we're going to assign a probability to every value that they can take. The way that we're going to work with continuous random variables is we're going to assign probabilities to ranges that they can take. Let's just go over some simple examples of things that can be thought of as random variables. So the biggest ones for building up our intuition in this class will be the flip of a coin, and we'll either say heads or tails, or 0 or 1. This is a discrete random variable because it can only take 2 levels. The outcome of the roll of a die is another discrete random variable because it can only take 1 of 6 possible values. These are kind of silly random variables because the probability mechanics is so conceptually simple. Some more complex random variables are given below. For example, the amount of the website traffic on a given day, the number of web hits, would be a count random variable. We'll likely treat that as discrete. However, we don't really have an upper bound on it, so it's an interesting kind of discrete random variable. We'll use the Poisson distribution likely to model that. The BMI of a subject 4 years after a baseline measurement is a somewhat random example I came up with, and in this case we would likely model BMI, body mass index, as a continuous random variable. The hypertension status of a subject randomly drawn from a population could be another random variable. Here we might give a person a 1 if they have hypertension or were diagnosed with hypertension, and a 0 otherwise. So this random variable would likely be modeled as discrete, or would be modeled as discrete. The number of people who click on an ad, again, this is another discrete random variable, but an unbounded one. But still, we would still assign a probability for 0 clicks, 1 clicks, 2 clicks, 3 clicks, and so on. So intelligence quotients are often modeled as continuous. When we talked about discrete random variables, we said that the way that we're going to work with probability for them is to assign a probability to every value that they can take. So why don't we just call that a function? We'll call it the probability mass function. And this is simply the function that takes any value that a discrete random variable can take and assigns the probability that it takes that specific value. So a PMF for a die roll would assign 1/6 for the value 1, 1/6 for the value 2, 1/6 for the value 3, and so on. But you can come up with rules that a PMF must satisfy in order to then satisfy the basic rules of probability that we outlined at the beginning of the class. First, it must always be larger than 0 because larger than or equal to 0 because we've already seen that a probability has to be a number between 0 and 1, inclusive. But then also the sum of the possible values that the random variable can take has to add up to 1. Just like if I add up the probability a die takes the value 1 plus the probability that it takes the value 2 plus the probability that it takes the value 3 plus the value it takes 4, 5, and 6, that has to add up to 1. Otherwise, the probability of something happening, right, that the die takes one of the possible values would not add up to 1, which would violate one of our basic tenets of probability. So all a PMF has to satisfy is these two rules. We won't worry too much about these rules. Instead, we will work with probability mass functions that are particularly useful, like the binomial one, the canonical one for flipping a coin, and the Poisson one, the canonical one for modeling counts. Let's go over perhaps the most famous example of a probability mass function, the result of a coin flip, the so-called Bernoulli distribution. So let's let capital X be the result of a coin flip, where x equals 0 represents tails and x equals 1 represents heads. Here we're using the notation where an uppercase letter represents a potentially unrealized value of the random variable, so it makes sense to talk about the probability that x equals 0 and the probability that capital X equals 1. Whereas a lowercase x is just a placeholder that we're going to plug a specific number into. So in the PMF down here, we have px equals 1/2 to the x, 1/2 to the 1 minus x. So if we plug in x equal to 0, we get 1/2, and if we plug in x equal to 1, we get 1/2. And this merely says that the probability that the random variable takes the value 0 is 1/2, and the probability that the random variable takes the value 1 is also 1/2. This is for a fair coin, but what if we had an unfair coin? Let's let theta be the probability of a head, and 1 minus theta be the probability of a tail, where theta is some number between 0 and 1. Then we could write our probability mass function like this. P of x is theta to the x, 1 minus theta to the 1 minus x. Now notice if I plug in a lowercase x of 1, we get theta, and if I plug in a lowercase x of 0, I get 1 minus theta. Thus, for this population distribution, the probability a random variable takes the value 0 is 1 minus theta, and the probability that it takes the value 1 is theta. This is incredibly useful, for example, for modeling the prevalence of something. For example, if we wanted to model the prevalence of hypertension, we might assume that the population or the sample that we're getting is not unlike flips of a biased coin with a success probability theta. And just to connect it to what we'll be doing in the future, the issue is that we don't know theta, so we're going to use our data to estimate this population proportion. In contrast to the probability mass function, which assigns probabilities to specific values for discrete random variables, is the probability density function, which is associated with continuous random variables. Just like a probability mass function has specific rules that it has to follow, a probability density function has specific rules that it has to follow. Specifically, to be a valid probability density function, a function must satisfy being larger than or equal to 0 everywhere, and then the total area under it must be 1. And then here is the basic rule of a probability density function. Areas under probability density functions correspond to probabilities for that random variable. So for example, if I say intelligence quotients are normally distributed with a mean of 100 and a standard deviation of 15, that implies that the population follows a specific bell-shaped looking curve, and that I'm assuming that the probability that if I were to draw a sample, the probability that a person from that sample has an IQ between 100 and say 115 is this area right here. Note again, our probability density function is a statement about the population of intelligence quotients in this case. It's not a statement about the data itself. Again, we're going to use the data to evaluate that assumption and to evaluate statements about the population probability, but inherently, whenever you say the word probability, you are talking about a population quantity. Interestingly, note when we model continuous probabilities like this, or probabilities for continuous random variables like this, the probability that it takes any specific value is in fact 0 because the area of a line is 0. This isn't a problem. This is just a quirk from modeling random variables as if they have infinite precision, but it doesn't gum up the works in any way at all. It turns out that the bell-shaped curve is a rather difficult density to work with, at least until you learn how, which we're going to be doing in a separate lecture. So let's work with a much simpler density right now, specifically one that looks just like a right triangle. So f of x equals 2x for x between 0 and 1 and 0 otherwise. And let's give some context around it. Let's say it's the proportion of help calls that get addressed in a random day by helpline is given by this. So what does this mean? This means that the probability that between 20 and 60% of the calls get addressed that day is given by this area. Well, let's ask the question, is this a mathematically valid density? I've plotted the probability density function right here. It looks like a right triangle. Notice the R code is given here and is given in the lecture slides itself because the slides are created using the Slideify format. So it's important to actually use Git to pull the course repository, and you can actually look in the RMD or R Markdown file and get all of the code for all of the examples, for all of the lectures. So at any rate, we need to discuss whether or not this probability density function is a valid probability density function. Notice it's always bigger than or equal to 0. And then secondly, let's calculate its area. Well, that's not too hard because it's a right triangle. 1/2 the area of the base, right, which is 1/2, times the height, which is 2. So 1/2 times 2 is 1. So the area is 1. So in fact, this is a valid probability density function. Let's go through an example of working with this density. What's the probability that 75% or fewer calls get addressed in a randomly sampled day from this population? Well, it turns out quite nice that this is just another right triangle that we need to figure out. So the height at this point is 1.5, because remember the function is just 2 times x. So at the point 0.75, the height is 1.5. And then of course the value of the base is 0.75. But then we divide it by 2 because it's 1/2 the area of the base times the height, and that works out to be 56% as shown right here. It turns out that this density is actually a special case of a known density called the beta distribution, and I give you the R code here for directly getting this probability from the beta distribution. Of course we don't need it because it's just working with triangles. However, in more complicated settings we're going to need these functions. I want to add that the letter P in front of a function asks for probabilities. So P beta is going to ask for the probability from a beta density of being less than 0.75. Here the 2 and the 1 are the specific parameters that turn it into the exact triangle that we're using right here, and you see that you get the same number, 56%. Certain areas of the density are so useful we give them names. For example, the cumulative distribution function of a random variable x returns the probability that a random variable is less than or equal to the value x. So it returns the probability capital X is less than or equal to little x. And this definition applies whether x is discrete or continuous. So remember, in our beta distribution that we just looked at, the p beta function in R always returns whatever the first argument is, the probability of being less than or equal to that. So in fact, whenever you do p density name in R, it is actually just returning the cumulative distribution function. The survival function is sometimes interesting to work with instead of the distribution function. It's just 1 minus the distribution function. So instead of the probability of being less than, it's the probability of being greater than. So imagine if we wanted the cumulative distribution function of the density considered before. Say, for example, we wanted to know what's the probability that 40% or fewer of the calls get answered in a given day, what's the probability that 50% or fewer of the calls get answered in a given day, and what's the probability that 60% or fewer of the calls get answered in a given day, given the particular model that we have right now, which is this right triangle as a population probability density function. Well, for any of those numbers, just looking at the picture, it's going to be very similar to 0.7, how we figured it out for 0.75. It's going to be a right triangle, so it's going to be 1/2 the area of the base times the height. That's always going to be 1/2 x, whatever x you're plugging in, times 2x, the height at that point, which works out to be x squared. So the function x squared takes the number that you want to evaluate and gives the probability of that percent of calls or fewer getting answered on a randomly sampled day. Okay, so we see that here when we plug in p beta, which is our cumulative distribution function in R, for these three values. The 2 and the 1 make it so that we're evaluating this specific beta density, and that works out to be 16%, 25%, and 36%. So on 16, so the probability that 40% of the calls or fewer get answered on a given day is 16%. The probability that 50% of the calls or fewer get answered on a given day is 25%. And the probability that 60% of the calls or fewer on a given day get answered is 36%. If you wanted the survivor function, it's 1 minus the cumulative distribution function, so it's 1 minus x squared. In the future, we're going to work with more complicated density functions, but it'll actually be easier because we'll just be relying, for example, on the p-norm and p-beta function like this instead of directly figuring them out. You've already heard of sample quantiles. For example, if you scored the 95th percentile, which is the 0.95th quantile on an exam, you know that 95% of the students scored worse than you and 5% scored better. These are the so-called sample quantiles. We're going to define their population analogs. So remember, in the sample quantile, if you wanted to find the 95th percentile or the 0.95th quantile, what you would do is line the observations from least to greatest, and you would find the exam score or the point such that 95% of the observation lied below it. The alphth quantile of a distribution function with distribution function f is the point x sub alpha such that f of x sub alpha equals alpha. That's quite a tongue twister, so let's see if we can draw a picture. If we were to draw a density, f of x, the distribution function evaluated at x, is the area below the point x, which is the probability that a random variable from this population is less than or equal to x. So you might think of it as a population of test scores, and it's an infinite population of students. And here, this would be the probability of getting a score for a randomly drawn student from this population of x or lower. The alpha of quantile is we move this line around until we find the point x sub alpha so that exactly alpha probability lies below it. That is exactly what we were doing with our data when we find an empirical quantile. We keep finding the data point such that, for example, 95% of the test scores lie below it. That would be the sample 95th percentile. Now we move the x point along until we find the point such that the probability of lying below it is 95% in this population distribution. Again, the percentile is simply a quantile with alpha expressed as a percent instead of as a proportion. And the median is the perhaps most well-known quantile, is the 50th percentile. We're going to use quantiles a lot, so it's worth reinforcing this point. So the 95th percentile of a population distribution is the point such that the probability a random variable is drawn from that population is less than that value is 95%, and the probability that a random variable drawn from that population is more is 5%. Let's work through our previous example. What is the median of the distribution that we were working with before? Remember that the distribution looked like a right triangle, and the distribution function, for example, if we wanted to find the probability that x proportion of calls got answered on a given day or less, that f of x, that distribution function, worked out to simply be x squared, where x has to be a value between 0 and 1 for it to make sense. In this case, we want to solve 0.5 equals f of x, which is equal to x squared, resulting in the solution square root 0.5. This is 0.7. So what this means is that on about 50% of the days, 70% of the phone calls or fewer get answered. And on about 50% of the days, about 70% of the phone calls or more get answered. We work with quantiles a lot, especially quantiles from the normal distribution. We almost never go through this process of working directly with the densities to calculate quantiles because the distributions we work with are common and this has already been done for us. In R, there's an easy trick. Basically, Q in front of the function name, function density name, gives the quantiles. So in this case, we know that this is a beta density. Well, we don't know. I'm telling you that this is a beta density. And so Q beta gives us the relevant quantile. Here we plug in 0.5. And remember, R takes the argument of the quantile as a proportion. So if you plug in 0.5, it will work. If you plug in 50 for 50%, it will not work. Okay, and the 2 and the 1 are the parameters that we haven't really fully described, but that you're going to have to just take my word for it that those are the parameters that yield the specific beta density that we're looking at. And when we plug this in, we get 0.7, 0.71, exactly like we got before. You might be wondering at this point, I've heard of a median before, but it wasn't this complicated. I just ordered my observations from least to greatest and took the middle, or the average of the two middle observations if I had an even number of observations. There you had a sample quantity. It's an estimator. In this class, we're going to build up not just estimators, but the targets of estimation, or the estimand. So in this case, your sample median is estimating your population median. So for example, a sample median from our previous example is if we were to sample a couple of days, calculate the percentage of calls that got answered on those days, line up those percentages, and take the middle one. That would be the median. We would think of that as a target, as an estimator of a population, sort of a true median percentage of calls that get answered. And there's of course a lot of assumptions that we're going to need to make to connect that sample to the population. However, we're going to be wide-eyed about those assumptions and we're going to formally develop them. So at any rate, in this class, to every estimator there will be an estimand. The sample mean will estimate the population mean. The sample median will estimate the population median. The sample standard deviation will estimate the population standard deviation, and so on. This is the formal process of statistical inference, linking your sample to a population.